Dear students, so in the last video lecture we have seen a simple example of calculation using unit load method. So now we are going to discuss another one which is a bit more tricky, and we are going to again use the same unit load method. So we have the equation unit load method. The expression is displacement is dx by ei, and if you want deflection at a point, we will be applying 1 kilonewton force. If we want rotation at a point, we'll be applying a moment 1 kilonewton meter. So these are basically our unit loads. This is the expression. We will be plotting a capital M figure and a small m figure. So all these things has been discussed in detail in the last video. So those who are having any confusion regarding those, please refer to that. So we are taking a sample problem. So now what we have here is a beam which is acted upon by a moment m at the end. Okay. So when there is a moment acting at the end, and say we have 3 points. Okay. Point A, B and C. This is L by 2, L by 2. Let the EI value be constant. So we are going to find 4 displacement values for this particular problem. Say YC, YB, that is displacement at B and C, rotation at C and rotation at B. Okay, that is rotation and deflection at the free end. Then we are calculating the rotation and displacement at the midpoint, that is point B. Okay, so we are going to start with the displacement values at the free end. So we are starting the calculation with YC. Okay, if we want YC, so we'll be having capital M figure and small m figure. Capital M figure is the given beam itself. Okay, this is point C. Now the small m figure is the beam and the load should be the unit load. So what is the parameter that we are calculating? We are calculating the deflection at C, that is YC. So if we want deflection, we need to apply a point force 1 kilonewton. So that's the point load, and C is the point where we want to calculate. So I'm applying the load at the C. Now we'll go with the table. That is SELOM, and as it is unit load method, small m also come into the picture. Now we are going to see how many segments are required. 1 point force, 1 point force, 1 point force, 1 point force. So just one segment is enough. So we are going to get the values. So segment 1, EI is constant, limit is 0 to L. Okay, the total length of the beam is L, so limit is 0 to L. Origin, I'm considering C because I have already discussed in a previous lecture that if we are having a cantilever, the best origin to take is the free end. So C I'm considering as the origin, so 0 to L, 0 to L. Okay, so we are going to calculate the moments at the section. So we are considering a section, a common section. So this is X, this is X. Okay, the X should be measured from the origin. Now let's see, what about the moment here? So when we are considering this case, I'm looking to the right because on the left I need reactions. I haven't calculated the reaction, so I'm looking to the right. So when I'm looking to the right, the moment magnitude is M. Now I want the sign. So I'm taking this point and consider as fixed. The moment is like this. So I applied it. Okay, what I'm getting is a hogging moment. So it is minus. Now I'm considering this small m. So what I have is 1. 1 is the force. X is the distance or the lever arm. So it's going to be X. So it is a hogging moment, hence it is minus. So the value I'm going to substitute in the general expression. So YC is integral m times m minus m times minus x, that is mx dx by ei, and the limit is 0 to L. So when I integrate this, I'm taking out the constants first. So integral x dx, that is x square by 2 in the limit 0 to L, So I'm going to get it as ml square by 2ei, which is the magnitude of the deflection at C. Now I want to see the direction. So the assumed unit load is downward. So the deflection what I'm getting will also be downward. If I get this value as negative, not in this case, in some other problem, if I'm getting the integral value as negative, it means that I assumed the load downward, but if I'm getting a negative value, which means that my actual deflection is upward. Here I got a positive value, which means the deflection is in the direction of the assumed unit load. That means downward itself. Now we are going with theta C. Okay, so capital M figure, small m figure. Capital M figure is the real beam or the original beam itself. Small m figure, I need to check what I want to calculate. I want to calculate rotation, which means I need to apply a moment, unit moment. The location is C. So at C, apply a unit moment 1 kilonewton meter. So I have it. Now I can think about the segments. How many segments? Point load, segment 1, point load, segment 1. Just one segment is enough. Now I will write the data in the table. So segment 1, EI is constant. Say free end I'm considering as the origin. So C is the origin. C is origin. This is the limit 0 to L. Then moment. Okay, so I need to take a section. I'm taking a random section and it is at a distance of x from the origin. Origin is C, so this is the distance x. I'm taking moment here. It is m. We have discussed how it became minus m previously. Now I'm considering this case. So here it is, the magnitude is 1. And what about the direction? The moment is like this, which means hogging. So this is also minus 1. Now I can calculate theta C. So limit 0 to L, just one segment, minus m times minus 1, that is m dx by ei. I'm taking the constants outside. So what left is integral dx, that is x in the limit 0 to L, which means the value is ml by ei. Now I need to think about the direction. So the assumed direction of point load was clockwise. So this is clockwise. So that's the deflection and rotation at the free end. Okay, this is the deflection at the free end. This is the rotation at the free end. Now we can continue and try calculating the rotation and deflection at point B. Okay, is a beam acted upon by a moment at the free end, which is a magnitude m. Now we are going to calculate the deflection and slope at this particular point. Okay, so let's start with deflection at B. So I'm going with m figure and m figure. This one is the same. Okay, here this is the critical one. So here what we want is the deflection at point B. So I need to apply the load at B. Okay, for whichever location you want the displacement value, apply the load at that particular point. Okay, so here we want deflection at B, so that unit load should be applied at B. The capital M figure remains same, there is no change. It is the external load figure. This is the unit load figure that need changes. So I got this. Now I can think about the table, the preparation of table. So it's going to be like S, E, L, O, M and M. Now I need to see, there is a small difference here. When I go try to put segments, here there is only one segment is required. But here we require two segments, right? Segment 1 and segment 2. So here we need to be careful. Here one segment, here two segments. In the earlier lecture I said that if either capital M or small m is having, whichever is having more number of segments, that need to be considered for the calculation. So this beam also we will have to divide it into two segments. Then only this particular procedure will work. Okay. So one was enough for capital M, but two are required for small m. Hence we are going for two in the capital M figure also. Now we are going to substitute. So I'm looking for the segment 1. So segment 1 is this one. Okay. And the EI value, it is constant. Limit is what we need to think about. So I can consider either this as the origin, this as origin, this as origin, or this as origin. Whichever I'm taking, it is fine. But whenever we are dealing with cantilever, I will always recommend you to look for the free end as the origin. So all the free end should be on the free end side. Better avoid it from the fixed end side. So B or C, whichever you prefer, you can take it as the origin. So I'm considering this point B as the origin. Okay. So I'm considering B as the origin. Even if we consider C as the origin, it is perfectly fine. If I'm considering B as origin, the limit of segment 1 is 0 to L by 2 because this is having length L by 2. If this is 0, this will be L by 2, considering this as the positive axis. Okay, you can consider this as positive, whatever, it's pretty easy. So I'm considering this as a positive, so it ranges from 0 to L by 2. So the limit is 0 to L by 2. Now I want to get the moment. So now I am dealing with segment 1. So the section should be cut in the segment 1. And the distance x should be from the origin. Here B is the origin, which is this point. So this distance is our x. Okay. If you are considering C as origin, then the distance x will be from C. Here B is the origin, so distance x is from B. Now let's see what the expression for bending moment. So if I'm taking a section here, what is the bending moment? Capital M. It is a moment, so no lever arm is required. Directly I'll be getting the value M. I need to have the sign convention. So it is hogging, hence it is negative. Now when I'm looking here, the moment is 1 into x. Okay, that is x. Okay, 1 times x, x. Sign convention, hogging. So negative. Now I need to think about the segment 2. Okay, earlier cases there was just one segment. Here we are having 2 segments. So in the second segment, so I'll be taking the section in the second segment. Fine. So segment 2 EI is okay. Now I need to consider the origin. There is no compulsion that we should take origin as the same in all cases. Here I can differ. So here I'm taking C as the origin. If C is the origin, what is the segment 2? Again 0 to L by 2. Right? If this is 0, this will be L by 2. So again 0 to L by 2. Fine. Now I need to take the moment, capital M. So it is again minus M, just like this. What about here? In small m, if I am looking to the right, there is no load at all. If I am looking to the left, there is load and there will be reaction. So I am not going to that side, I am looking to the right. There are no loads, which means the moment is basically 0. Fine. So I have the table data. Now just substitute the condition. YB is equal to mmdx by EI. So limit is 0 to L by 2. I am going with the segment 1. So the value of M, capital M, small m, multiply, I am going to get mx dx by EI. Okay, limit is 0 to L by 2. That is for the segment 1. Now for segment 2. Segment 2, again the limit is 0 to L by 2. When I multiply capital M and small m, I am going to get 0 dx by EI. Okay, this part is for segment 1. This part is from segment 2. Okay, and we can see that this reduces to 0. So what left is 0 to L by 2 mx dx by EI. Integral of x dx is x squared by 2. So it is m by EI x squared by 2 in the limit 0 to L by 2, which will give m L square by, okay, there is a 2 and another 4 comes from this L by 2 whole square, so 8 EI. Okay, that's the deflection at point B. And what about the direction? The assumed load is downward, hence downward. So that's the deflection of point B. Now we are going to talk about the slope of point B. Okay, so I need to get the slope. So theta B, right? So without any further ado, I'm just going into the small m and capital M figures. So this is the capital M figure, and here I have the small m figure. So in small m figure, I want rotation at B. So this is the point B. Okay, this is the point B. So at point B, I want rotation, which means I need to apply a moment of 1 kilonewton meter at point B. Okay, so this is my capital M and small m. Now I'm going with the table. So S, E, L, O, M and M. So what about here? How many segments will be required? Point load, 1 segment, 2 segments. So here I require 2 segments, here only 1. So there is no way, we have to go for 2. Whichever is higher, we need to go with that. So here also we require 2 segments. So we are dealing with the segment 1. Okay, EI is constant as given in the problem. So again, the limit comes into the picture. So I need to decide where the origin should be. So I'm considering B as the origin. If B is the origin, the limit of segment 1 is 0 to L by 2. Right? So I need to take the section. I'm taking a section and I'm marking the distance x from the origin, which is B. So what is the moment? In this case, it is minus m, which I have discussed earlier, the same value. What about here? Here it's going to be the magnitude will be, if I'm looking to the right, I'm having a moment 1. What about the direction? It's a moment like this, which means moment like this, it is hogging. So it is minus. So that's the segment 1. I'm going with segment 2. So I'm taking a section in segment 2 somewhere here. Okay. Now EI is constant in segment 2 also. I'm considering C as the origin. Okay, this point I'm considering as the origin. So the limit of segment 2 is 0 to L by 2, just like the previous one. Now I need to take the moment. So what about the moment? Here it is minus m, just like before. What about in the small m? In the right, I don't have any load at all, which means it is 0. Now I can calculate theta B. So theta B will be, there are 2 segments, there will be 2 sections. So 0 to L by 2, I'm talking about the first segment, range is 0 to L by 2, m into m. So it becomes m dx by EI plus the second segment, the range is 0 to L by 2. So limit is 0 to L by 2. Then mm minus m times 0, which is 0 dx by EI. So we can see that this becomes 0. This is contribution from segment 1. This is contribution from segment 2. Now when I integrate, so this part goes away. What left is this. I'm taking out the constant. So m by EI is outside. Then integral dx, that is x. So x within the limit 0 to L by 2, which means that ml by 2 EI is the magnitude. What about the direction? The assumed unit load was having a clockwise direction. So the rotation, what we are getting is also clockwise. So hence we have the deflection and slope at point B. And in the first part, we have seen the values of deflection and slope at the free end. Okay. Thank you.